Good afternoon. Thank you for joining us again in the lecture series that is basic inverter topologies and PWM techniques as applied to power electronic based converters and inverters. So just to recap what we have done yesterday, we have started with basic voltage source inverter topologies. Starting single phase, we have covered half bridge single phase inverters and full bridge single phase inverters. In both the topologies, we have seen what is the maximum capability an inverter can be operated. So that is only possible if we operate in square wave mode. So that is you turn on the top switch for half the cycle and you turn on the bottom switch for second half of the cycle. So if we do square wave modulation, we get the best what an inverter can offer in terms of output AC voltage. So we have seen that for a single phase and three phase, even both of them, the maximum peak output voltage of the AC will be 0.6366 VDC. If we go for sine, so what is the problem with square wave modulation? It is fantastic, you are getting this kind of output voltage. But we have seen that if you output this kind of voltage, which is a basically typically a square wave kind of thing, if you take the harmonic, how we analyze the AC output waveform, the perfect measure is by doing a fast Fourier analysis of the waveform. If you do fast Fourier analysis for a square wave waveform, it will have all kind of harmonics, so especially it will contain all low order harmonic. So it will have first, then fifth, sixth, and so on. So these are, and the TS waveform will be very poor. And if you apply this kind of waveform for a RL load, which is typically our maximum kind of loads, have those characteristics, they will have a non-sinusoidal current. We don't want those kind of waveforms. So therefore we go for sine triangle modulation. If you do sine triangle modulation and you apply those kind of switchings to the inverter, you get a perfect, nearly perfect AC voltage at the output side, and thereby we get sinusoidal currents on the output side. So we have extended our understanding of single phase for a three-phase half bridge converter as well. So we have seen in a three-phase half bridge topology, again we would have started with what is the maximum output voltage you get across phase to neutral if we apply square wave modulation here as well. So we have seen that if you apply square wave modulation, the per phase to neutral voltages will be of this nature, and because of this, so actually it can be seen that you have 6 steps in one cycle of a AC waveform. What that means? It means that you have a dominant 6th order harmonics. So when we have done the FFT analysis of this waveform, we have seen it is containing 6M plus minus 1. It will not have triple harmonics because it is a three-phase balanced circuit. So it will not have 3rd, 6th, 9th and so on. It will also not have even order harmonics because it has a odd and even symmetry. Therefore, we will have 1, 5th, 7th, 11th, 13th, 17, 19 and so on. We have also seen in the simulation that if you apply this kind of waveform for a, let's say, a three-phase induction motor, the waveform of the current will not be good. It will also have a dominant 6th harmonic, which will ultimately result in a torque waveform which is not pure DC. So torque waveform will have dominant 6th harmonic ripple over a constant average DC torque. So today And then we have also seen, if we apply sine triangle PWM for a three-phase half bridge inverter, then you can get a fundamental voltage which is nearly sinusoidal, and the harmonics will be pushed to the switching frequency level. So let's say if you're switching the inverter at a switching frequency of 10 kilohertz, after fundamental the next harmonic will be at 10 kilohertz, 20 kilohertz, and so on. And since the harmonics will be is at such a high frequency, it will not have any effect on the fundamental, hardly anything. Now we can neglect it actually if you are switching anything more than 10 kilohertz for 50 hertz AC waveform. So we have seen if we apply a sine PWM AC voltage, a three-phase AC voltage to a three-phase induction motor, the currents are almost sinusoidal. It's sinusoidal itself. The small harmonics because of switching frequency will be easily absorbed by the leakage inductance of the induction machine. This will result in a perfect, almost DC torque in the motor shaft, and there will be smooth running of the motor, and it's good for the life of the motor. So definitely, if you are going for sine triangle modulation, we are getting down lot of benefit in terms of fundamental voltage, the quality of output current, and the torque. But what price we have to pay for that? So we have to see that if we go for square wave mode, the peak output voltage, the peak output AC voltage will have a magnitude of 0.6366 VDC. But if we go for sine triangle PWM, so if you take the ratio, so the ratio of output voltage what we get from sine triangle to the output voltage we get from square wave mode is of the order of 0.78. So as I mentioned toward the last part of the lecture, we are getting it almost 22% less voltage at the output side. So this is the price we have paid, for getting a quality voltage and current on the load side. So later we have also analyzed, the phasor analysis. Means if we represent a resultant vector as a combination of three phase voltages, and if we plot both the square wave mode and a sine triangle mode, the trajectory of the resultant voltage phasor, we have seen it is like this. So this is for square wave mode, and the length between this and this is VDC, and even this is also VDC. So it's a hexagon. If we apply sine triangle modulation, so basically this is nothing but trajectory of the resultant vector. So what is the trajectory of resultant vector for a sine triangle PWM? So we have seen that it is somewhere here. This is for sine triangle and this is for square wave. So the radius of this is 0.75 VDC. So how we got it? The per phase peak, it's VDC by 2, and if for space phasor, it is multiplied by 3 by 2 into VDC by 2 is 3 by 4 VDC, which is nothing but 0.75. Here is very important point to note. So sine triangle is a almost linear. You get perfect sine waves because the trajectory of Vs is circle. But if you see the trajectory of square wave mode, it is not circular. So this trajectory is basically non-linear. So it is even understood from waveforms. It has dominant 6th harmonic. You have 6 notches. So can there be if you apply sine triangle modulation and if you apply square wave modulation, there is a region to be still explored. What about that area? Can we reach this area from any other point of view, from any other modulation technique? So the answer is yes. There is one modulation technique which can cover the total region, right from 0 to full hexagon. So the method is called so what this method does. See, these methods operate the inverter in a different way. It's not similar to sine triangle modulation. So it analyzes the inverter and its output states in terms of space vector. Actually, it as obvious from the word space vector. It tries to understand the switchings what we do in an inverter with respect to its space phasor or space vector, and then try to evolve a strategy where we can cover all the region of the hexagon. The circuit diagram of 3-phase half-bridge inverter, we have 6 switches. S1 to S6, and also we know S1 and S4 are complement, S3 and S6 are complement, and S5 and S2 are complement. So basically, if you try to see this circuit in a slightly different way, So R, Y, B are, the poles of the inverter. And we have seen that RO, YO and BO are pole voltages. And depending on how the switches are turning on and turning off, so this can have only two switching states, either VDC by 2 or minus VDC by 2. For all the three things, all the three pole voltages can have only two states, either VDC by 2 or minus VDC by 2. So if let's say if we want to write, combination, so if I make a set VRO, VYO, VVO, each can have two states. Suppose we call them as 1 and 0. So if we have two states and three combinations, together we will have 2 raised to 3, which is 8. Actually it's called, switching state set. So basically it's a set of switching states. So we can have 8 possible combinations. So what are they? It can be 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, 0, 1, 1, 1, 0. So basically you have 1, 2, 3, 4, 5, 6, 7. So let us try to understand from a space point of view what are the state means, So here this is basically top switch is connected, bottom switch is connected, bottom switch. So this is plus minus minus means 1 0 0. This is plus plus minus. Plus plus minus means plus is VDC by 2, minus is minus VDC by 2. So this is 1 1 0. This is minus plus minus. So 0 1 0. So similarly this is minus minus plus, which is 0 0 1. This is plus minus plus, which is 1 0 1. This is plus 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 is 1 1 1 minus 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 0 0 0. So in this combination of 6 sets, so this is called V1, V2, V3, V4, V5, V6, V7 and V8. Don't confuse this with this. You know, there is a reason why this is called 1 2 3 4 5 6 7 8. So these states are called zero states. So in this, all the three phases either will be connected to negative DC bus or positive DC bus. So since all the switches are connecting, either S1, S3, S5 are on, or S4, S6, S2 are on. So in both these cases, there is no output voltage. So that's why it's called zero vector. And all other vectors are called, so we will see this one by one. So if we try to put this V1 to V6 and V7 and V8 and try to map them with their space phasors, it will look like this, which is very similar to our understanding from a square wave mode. So the this is V1. So V1 is located V1. So basically, what is V1? So V1 vector is nothing but VDC angle 0. V2 vector is VDC angle 60 degrees. So this one. V3 is VDC angle 120 degrees. So what is V1? V1 is plus minus minus. V2 is plus plus minus. V3 plus plus minus. Similarly, V4 is VDC angle 180 degrees. V5 is VDC angle 240. Is 300, where V4 is minus plus plus, V5 is minus minus plus, V6 is plus minus plus. If we see this, basically this is V1, this is our V2, this is our V3, this is V5, this is V6, this is V7 and this is V8. So how the switching states, which is nothing but this one, this switchings has transformed to, we like to understand how it happened, how the switching states we are calling V1 to V6 and V7 and V8 have got these angles associated. For that we have to use a space vector derivations. So any three-phase system can be represented by a equivalent two-phase system, which is generally named as alpha and beta. So alpha will be along the first axis and beta will be leading the alpha axis by 90 degree. So since we know, we can write as this can also be written as where this is and theta is tan inverse V beta by V alpha. So using the combinations what we have used, so this procedure requires two things. What we know is pole voltages. So for the pole voltages, we have to find what is VRN, VYN, VBN. Then only we can do this transformation. So what is the procedure? You take the switching state, which is nothing but transform them to line to line phase to neutral voltage and then transform to so for this transformation is known. We now have to learn how to do this. So generally the formula is So let us do this exercise. This we see yesterday. So if we open this, similarly we can write. So this is direct formula for getting from pole voltage to neutral voltage. So if these are the switching states, so this will be then VBA. If you plot V alpha and V beta, V and this will be 0. Which means Therefore, you can say that the switching state V1 means space vector Vs Vdc angle 0. So this all, converting all states to the space vector can be done. So we have seen how these switching states, this converts to this converts to this, and so on. So basically we can see that what we have done now, we have done, conversion of all switching state combinations respective space phasors, and we have plotted it in a space. And if you join the edges, we'll get a hexagon. So you join this turns out to be a hexagon. So, understanding this by switching states and vector combinations, there is a purpose. So this will help us to understand technique, what is known as space vector. Switching using these vectors is what is known as space vector modulation. So going forward, generally this is called sector 1, is called sector 2. So V7 and V8 are zero vector which doesn't have any magnitude in any direction. Purpose of dividing the hexagon in 6 sectors. So when we apply, let's say I want to apply 3 AC voltages to the load. So once we know the 3 AC voltages what we need to be applied, we know what is the space vector for that. So what is Vs? Vs is a rotating vector. So let us try to plot this here. So what we need to understand, how to get this using the combination of so basically we have a triangle. to obtain the radius, let's say for a sampling time of Ts, use a combination of applying V1 time, V2 for T2 time, the vectors for rest of the time. Where T1 plus T2 plus T naught is equal to Ts. So these are also space vectors. So if we resolve all the vectors, that is Vs vector, V1 vector and V2 vector. We'll get two equations, and it will help us to find what period of time we need to be applied and what duration of time vector V2 will be applied, and the rest of the time is should be given for 0. So you can see that if you apply in this fashion, the average resultant vector Vs can be arrived. So this is a method where you apply switching vectors to get the resultant depending sector you belong to. The active vectors will vary. Zero vector more or less will vary into half here. Why? So that only one transition in each phase. you apply, this is a method of space vector modulation. So in modulation cover all region of the hexagon, but in sine triangle modulation, you can cover only portion of the. So we can as well the three phase voltage references for SVM even by adding third harmonic to sine triangle PWM. So the effect of space vector modulation can also be obtained by sine triangle PWM. You just add and give and compare it with so now we have completed the space vector modulation for a three-phase voltage source converter. We have seen, we have studied three modulation techniques. One is square wave modulation, sine PWM modulation, and space phase modulation. So this is basically a gist of whatever we have studied with respect to three-phase inverters. So let us now take questions asked by different participants. change in voltage of the inverter? It will not. See, output voltage is generated by a constant DC link voltage, so it is independent. So if there is a change in any load dynamics, it will only affect the load current. Voltage will be, rigid. Somebody asked, what is mean by square wave inverter? See, there is nothing called a square wave inverter. Basically, if you operate the inverter in square wave mode, where you don't switch, you turn on the top switches for half the cycle, you turn on the bottom switch for next half cycle. This mode of operation is called square wave mode. It is simple to implement. So somebody asked, what is the region of operation of SBM? So we have just two regions, as long as we are operating a circular region, it's called linear range. And if we are outside the circle, it is non-linear. So we have covered this here, So this green circle, actually whatever inside the green circle is linear range. But here you cannot apply a Vs vector which is circle. So this is non-linear range. So what is UPS? UPS is inverter plus battery. You all know that all switches has anti-parallel diodes for handling, when there is no power supply. With the supply, this will work as an inverter. So the battery, if battery voltage is available, this will generate three-phase voltages. But let's say supply is available now, so we don't need this UPS to function. Rather, we will use the supply and this rectification to charge the battery. So the switches will be out of picture in rectification mode, and everything will be in place for a inverter mode. So linear range. So somebody asked linear region or non-linear region. Definitely region preferred. You have sinusoidal currents in the load, and if you apply for motor applications, the torque is smooth. So basically, why we require heat sinks in inverters? So inverters, are not, are they dissipate a lot of power. Uh, so you have basically two kind of losses. One is conduction loss. So that is because of, that when the device is on, there is a resistance involved. It's not zero. So let's say in the case of MOSFET, we know the on state resistance is called RDS on. If you pass any current across it, will have I square R losses. And there are losses which is called switching losses. So it depends on what kind of load you are switching on and switching off. So there is, you might have heard of snubbers. So snubbers are used to uh, reduce switching loss. So it will basically this turn on and turn off snubbers helps to reach the current and voltage transients such that the switching losses comes down. But if you don't have snubbers, there can be a huge switching loss. So what are the three states of charging? I think probably the questioner is looking for the three states of charging for the battery. So battery has three states of charging. It's called trickle, and actually I'm not an expert on that. So basically, the battery has to be charged at a particular current rate. So depending on the condition of battery, if battery is highly discharged, the rate of charge should be different, and when it is close to full charge, the rate of charging should be different. So basically, the three stages of charging is referred to the battery charging. So for for that understanding that, we have to understand the SOC of battery. Uh, SOC means state of charge of the battery. So there are different methods to estimate the same, and based on that you have to apply the different states of charge. So somebody has asked whether 0% harmonics is possible. So harmonics, the percentage of harmonics reduces as we increase the switching frequency, because we are shifting the quantum harmonic power to higher switching frequency, so the percentage will be less. But 0% not possible. We need some harmonic because switching is happening. Discuss tomorrow. We'll discuss tomorrow in detail. Okay. So let us rejoin tomorrow afternoon So tomorrow we'll what is the basis of multi-level converter and what is current source inverter. So we will see these topics tomorrow. So please join us tomorrow afternoon at 2 o'clock. Nice evening.